of social distancing and wearing masks and things like that when you're out and about. We'll see what happens over the next few months.
Almost half of these patients have recovered, or not that much recovery.
It's a good question. I'm not sure what the recovery rate has been. I know that we are well over about 1.5 million infections that have been so far. I don't know the exact number of who has recovered with 100,000, right at 100,000 deaths as of today.
Sir, in 2 minutes the session will be starting, sir.
Very well. And how are you suffering a number of high infections there from COVID-19? How's it going there?
No, the region we are saying now, it is COVID-free. So all patients have been recovered, and there is no new. Past 2 days are now, it is past 1 week it is recovered, but recovery is very high here. 90 is in the 90% of the patients they have recovered, and the recovery rate in India is high. Some states, some regions they are already COVID free. Some regions still there. Patients are there, but recovery rate is quite high. Almost 70-80%, up to 90% of regions they have recovered.
Okay.
That is good for India, but still patients are there. We are taking a lot of treatment, and we are inside the house and different.
Okay.
Yes, sir. Sir, we are ready to go. First of all, I would like to welcome our participants and our chief guest. And this is a good evening where we are together to learn about our NASA's small cell and Kepler mission. So I request our HOD, head of the department, Dr. Dharmendra Singh Chand, to deliver the welcome address. Yes, sir. Please go ahead.
Thank you very much. Good evening, all. On behalf of Chandigarh University and Department of Aerospace Engineering, it gives me an immense pleasure and to introduce and welcome Mr. Roger Hunter, Project Manager, NASA. Mr. Roger has 4 decades of experience in defense, space, and commercial department. Mr. Roger Hunter played a key role in GPS, Kepler mission, small set technology of USA, all these departments. Mr. Roger served more than 7 years for Boeing in the capacity of site and sustainment manager. He was associated with US Air Force from 1981 to 2003. Hunter holds PG degree in air power, space operations. Above all, he is very good mathematician. I welcome you, sir, for the session, and thank you for accepting the invitation to deliver the lecture on the topic. I request you to proceed for the webinar.
Yes. We have one more video to show about the basic introduction about Roger Hunter. I would like to play that.
Okay.
So, can you able to see my screen, sir?
Yes.
Sure.
Good evening, ladies and gentlemen. Thank you so much for joining this amazing session with a dynamic personality who is the project manager for NASA's Kepler. the first nation capable of finding the habitable planets in the Milky Way galaxy outside our solar system. And he also served in US Air Force, focusing on space operations with the project manager microsatellite technology demonstration for the Air Force. Later, he was also joined in Boeing and worked in an integrated defense systems by more than 2 engineers and technicians in the global positioning system in and control system. None other than Mr. Roger Hunter, who is experienced in space system operations, deployment, acquisition, maintenance, and sustainment. So learning is like Newton's third law: learn and invest. Stay tuned with us and learn. Good.
Thank you, sir. Thank you for joining with us, first of all. I request Rohan sir to start the session. I will be giving the presenter role to you. You can start the session.
Okay, thank you. Can you see my desktop?
Yes, yes.
Thank you so much for the introduction. I am asked to speak two subjects today. My current position as the program manager for NASA's Small Spacecraft Technology Development Program. And towards the end of the session, I will speak about the legacy of the Kepler mission. And I was the program manager for the Kepler mission for a number of years before I assumed the position that I am in today for the NASA Small Spacecraft Technology Development Program. Let me begin by just thanking the sponsors for inviting me today to give a talk with Chandigarh University. Unfortunately, of course, we're suffering from the COVID-19 pandemic. I would love to visit you in person someday, but today we will do the webinar instead. Let's talk about NASA small spacecraft technologies and how they're actually oriented. There's three different areas, and I work primarily in the one you see on the screen that's on the left. And it's in the technology development area, which will allow technologies to be matured that are coming out of either academia, small businesses, other government agencies, or other NASA centers, so that they may be instantiated in future exploration or science missions that you see on the right. A couple of examples of the ones you see on the right are things like the Marco mission, which were two CubeSats that were 6U in size that escorted the InSight lander to Mars and relayed its entry, descent, and landing signals back to Earth as the InSight lander was making its final entry, descent, and landing onto the Martian surface. We are looking at using small spacecraft and small spacecraft technologies to enable future science missions, and we have some on orbit now, one of which is called Cygnus, CYGNSS, and that one is a weather observation satellite. So we, NASA, are starting to embrace small spacecraft and small spacecraft technologies into the way that we conduct our science and exploration missions. But in my current position, I'll be focusing on the column on the left on space technology. Why do we do this? The intent is to expand our capability to execute unique missions through rapid development and demonstration. When you think about how far the technology and electronics revolution has brought us, particularly if you look at your smartphone and the capacities and capabilities of that, why can't we use some of those technologies in the small spacecraft that we build today? And that is what our intent is, to take advantage of commercial off-the-shelf technologies and put those inside small spacecraft and use those for conducting science or exploration missions. That allows us to reduce the cost of these missions. It also allows us to reduce the time that it takes to build these spacecraft. It reduces the time to get them in orbit. It also enables new types of mission architectures, just as the one I just mentioned, which an InSight lander, a mothership carrying 2 CubeSats along with it to Mars. New destinations are also enabled by the development of these types of technologies. We are looking at concepts in which we send additional CubeSats or very small satellites with a mothership off to a destination such as Enceladus, the moon that orbits Saturn, around which the Hubble Space Telescope and the Cassini mission have observed water geysers coming off of that moon. Now, I would like to show you the technology pipeline. Where do we get this? I've sort of mentioned this a little bit earlier. Our technologies come from different areas. They come from university partnerships. And NASA, we have a solicitation annually with universities across the United States, and we indicate which focus area we want that year, whether it's power, propulsion, communications, or processing capabilities. And we solicit the best ideas from the universities. We also have another initiative in which we work with small businesses. Those are called small business of investigative research, in which we harness the pace of innovation that is coming out of those small businesses. And sometimes we also partner with large businesses like Northrop Grumman or Boeing for some small spacecraft technologies. We have other things that we call public-private partnerships, in which a company which is investing in a technology that's part of its business base will reach out to NASA, and we will share the investment costs with that company to see if we could get the technology that they're working on developed to a technology readiness level that will enable it to be used for science or exploration mission. And then when we think the technology has reached a certain level, although it will not have yet been used in a science or exploration mission, we will conduct a demonstration with it to ensure that the technology has matured well enough so that when we do put it in a science or exploration mission, it will work properly. The next two charts just gives you an indication of the breadth and scope of the small satellite technology partnerships that we have been conducting with universities over the last several years. We have participated with 28 universities in the US across 19 states. And you can see the amounts of awards on the bottom. It's for universities or for big businesses. This may not seem like a lot of money, but when you're working with universities, we get more bang for the buck, probably because they're using graduate students who are provide cheap labor. But they work very well with us, and we enjoy working with the universities because there are some engineers that come out of those universities that we end up eventually hiring into NASA. So this is a way to also not just get a technology developed, but also a way to observe the engineers that are coming through the pipeline that we would like to hire in the future. Wow. There's this next chart just gives you an example of the number of technology selections that we made in our most recent selection. I don't want to dwell on this, but it just gives you an indication of the value of the technologies that we're getting from these universities. And the ones that you see here, of course, are oriented towards the items mentioned before. They're either helping us improve the power of these satellites, improve the propulsion, improve the communications, or improve the processing of them. And the reason for that is we want to be able to get small satellites, which have been mainly constrained to low Earth orbit, out into cislunar and planetary space and beyond. So let's talk about some recent missions that we have completed. And there are two on this page, and I'm going to spend a few minutes talking about each one of these, because these were recently successfully completed. The one on the left is called the Integrated Solar Array and Reflector Array Antenna, and one on the right is an optical communications and sensor demonstration. Of course, both of these were oriented toward the communications aspect of improving the capabilities for small spacecraft. And you can see a hand in the left one for size scale and some fingers on the right one, because the one on the left is about 3U in size, and the one on the right is about 1.5U in size. I'm going to talk about the one on the left first, and this one is 3U in size and demonstrating that flat panel antenna that you see that the engineer is touching there. It's not the usual concave antenna that you see that, for example, that you would use for a dish network for receiving your television channels at home. And this one was also transmitting the Ka band communications. This was the first time that we had put Ka band communications into a spacecraft that is this small. When I was on the Kepler mission, we had a Ka band communications on Kepler, and that was actually the first time we had used Ka band communications on a rather large spacecraft. With ICERA, that was the first time that we had used Ka band on a very small spacecraft. And if you look at the title, it says integrated solar array and reflector array antenna. On the other side of that panel were solar cells, and hence we were demonstrating that you could have a panel that had antenna material on it on one side and solar arrays, solar cells on the other side of the antenna. Something interesting happened with this one. Right before we were to launch, the Aerospace Corporation approached us and said that they had a multispectral imager that they would like for us to fly, and we had sufficient time to integrate that multispectral imager into the spacecraft, and we did. And I want to show you some photographs from that shortly. The one on the right, this was there were two of these that we built, optical communications demonstration, and the intent was to demonstrate laser communications from a very small spacecraft from low Earth orbit. And this one also worked quite well. In this one, we worked with the Aerospace Corporation, which is headquartered in Los Angeles, California. And the demonstration was to show that we could zap a optical telescope on top of their building multiple times. And we were able to demonstrate that and also transmit 200 megabits per second data rate using this particular system. So this is one more example of how small spacecraft are dramatically changing and also improving so that we could improve the communications data rate of a number of these small satellites. There was something we did with both spacecraft, though, which was not planned in the beginning. I want to show you some photographs that were taken with the multispectral imager we placed into the ICERA spacecraft, which is the one on the left, just to remind you. But this was a very small instrument, and it took up only 1/3 of the space of that spacecraft. You may have remember the news about the large forest fires we had in California in late November 2018. And the images you see on this chart here show you those forest fires. I don't know if you can see my cursor. I hope that you can. I'm pointing at the image that's on the left, and I'm circling an area that is the town of Paradise, California, which was completely wiped off the face of the earth when the forest fires marched through there. Many lives were lost, and a lot of property was lost as well. And it was actually kind of sobering to see this as the ICERA spacecraft was flying over this at night, and we were taking these photographs, that you could see the extent of the fires in this area. Particularly, we could see the burning embers of what was left of the town of Paradise, California. Now, this video I'm going to show you, I'm hoping that you are able to see the animation. Now, I'm back to talking about the optical communications and sensor demonstration. You can see water propellant being expelled from this particular spacecraft because both spacecraft, we actually did place a propulsion system on board. It was water-based, and we simply heated it up and expelled water vapor to provide the propulsion for both spacecraft. After we completed the laser demonstrations, we actually used those propulsion systems to do proximity operations around each of the spacecraft. So there was a secondary objective. Besides demonstrating the laser communications, we also demonstrated proximity operations of those two spacecraft. At one time during their mission, they were as far apart as 476 kilometers. And with the propulsion systems, we were actually brought them back to where they were only 6 meters apart. And we added one additional demonstration initiative at towards the end of the mission. There was an RF antenna between two spacecraft, and we're actually able to use that for using one spacecraft to command the other to move and demonstrate that you could have propulsive maneuvers completed with one spacecraft relaying those commands through to the other one. Now, this was, there's another one I'd like to show you here, but I want to set this up. This was a demonstration that used the laser-equipped spacecraft with the multispectral imager on the ICERA spacecraft. That multispectral imager was called Cumulus, and I forgot to tell you that on the other chart, but that's what it's referring to here. When we were finished with the ICERA demonstration, we actually decided to use the multispectral imager for a different type of demonstration. Both the spacecraft were about 2,200 kilometers apart in this image, and I'm going to run the animation shortly for you. But you see a dot here that's going to be moving across the face of the screen from about the 10 o'clock position to about the 4 o'clock position. It is not a UFO. That is simply a star that's radiating very hot in IR, and you're looking at it using the multispectral Cumulus payload that's on board ICERA. Right in the middle of the screen, what you'll see light up will be the OCSD laser, which we aimed at the ICERA Cumulus payload from that distance of 2,200 kilometers. And let me run that demonstration for you. And you will see the light up right in the middle there. And it demonstrated that you can actually take a very small spacecraft and point it at another one and laser it. And this was a risk reduction demonstration to show that we would be able to provide sufficient tracking between two spacecraft classes that are at that distance and able to point a laser at one and laser it. And this is important for us because we would like to have interlinked spacecraft in the future that use optical capabilities so that we could provide much more data exchange between spacecraft. And we thought this was actually kind of an interesting demonstration. And we put this on the NASA main Twitter feed, and we got a lot of good comments on the technology demonstration. But the Flat Earth Society also commented on it, saying that the limb of the Earth here was a fiction, and that this is all fake news. And so we had a little fun with them about this particular demonstration by just telling them, no, the Earth is not flat, it's round. We always known that. That was just a little humorous thing that happened with our Twitter feed and the Flat Earth Society after we released the results of this particular demonstration. And I want to run this for you one more time so that you can see right in the middle, you'll see the laser light up. We did several repeats of this particular demonstration. The first time we just lased or moved the laser across the focal plane of the Cumulus sensor on board ICERA. There were other times we stayed locked on for over 3 minutes. Here are some other upcoming demonstrations, and these will be launching later this year and early next year. The one on the left is called Pathfinder Technology Demonstrator. That is a 6U class size spacecraft, and it was meant to have 3U of space reserved on board for new payloads that we are developing, new technologies that are developing that could be used for future small spacecraft missions. And I've listed a number of those at the bottom. One is a water-based thruster. One is a brand new attitude determination and control subsystem that is built by the Ball Aerospace Corporation. Number 3 is a high-band laser communication system. I mentioned earlier that the one that was on the OCSD, or Optical Communications Sensor demonstration, was capable of transmitting 200 megabits per second. This one we're working on with MIT and Lincoln Labs, and this one is capable of 200 gigabits per second. So we hope to demonstrate that particular payload using the Pathfinder technology demonstrator bus that you see here on the left within the next 2 years. And there will be another reflector array antenna we intend to fly, and that one's built by JPL, and it's the acronym is called OMERA. And the last one I'm kind of interested in, and it's called LISA-T, which stands for Lightweight Integrated Solar Array and Transceiver. It's a dual-purpose payload that you can fold into 1U of this 6U space on the Pathfinder technology demonstrator. On orbit, when the door opens on that 3U payload space, then that 1U LISA-T demonstration unfurls, and it has S-band patches all over it, so it gives you S-band communications, but it also has some very unique solar cell material, and we are hoping to get up to as much as 600 watts out of that 1U origami folded demonstrator. Now, the one on the right, what you're seeing here are two 3U spacecraft that are docked together. So CPOD, or CubeSat for Proximity Operations Demonstrator, is a demonstration of two 3U size spacecraft that are launched together, and after they are deployed from their dispenser, they move to a certain distance, and then they will separate and drift apart for a number of kilometers, and then they are turned on, and then they're told to find each other, and then they will perform maneuvers until they close enough, and then they will autonomously dock. And there's two mechanisms for docking. One is a mechanical, so there's little fingers that you see between the two spacecraft. It's maybe hard to see it on this. You can barely make out the fingers, but it also has an electromagnetic docking mechanism. So as they close the gap between the two, and as they're approaching, the electromagnets are also turned on, which will start hopefully attracting them even closer to each other when they're within meters, and then they will dock with one another. So that one will fly hopefully by the end of this year. I'd like to talk about some other demonstrations that are coming up. The one on the left is a very rapid demonstration. Of course, NASA, we love our acronyms, and so this one's called VREX. And these are three 1U size spacecraft that will demonstrate ranging between two spacecraft and some coordinated measurement technologies, and just using three 1U spacecraft for a swarm demonstration. The second one you see from the left is called the CubeSat Laser Intersatellite Crosslink, known as CLIC. And this is a technology demonstration we're working on with the Massachusetts Institute of Technology. You may recall earlier that I mentioned that optical communications and sensor demonstration was a demonstration of optical communications from spacecraft to ground. With this one, we're going to demonstrate the laser between two spacecraft, and they will both be exchanging information with each other. The next one is the Advanced Composite-Based Solar Cell System, ACS3, and this one is about, when it unfurls, about 81 square meters total of flat space, and you can see the 12U space that is right in the middle of this. The technology is not in the sailing material, it's actually in the booms, which is a new composite material that NASA Ames Research Center is working on with the Langley Research Center. And this one should be flying next year as well, but the technology we're demonstrating is in the composite booms, because when you start getting metallic booms at this length, they start warping and twisting in space, and we wanted a material that does not warp and twist when you're in the space environment. The next demonstration you see on the right is called Starling. If you may be familiar with the birds swarms that are called starlings, hence the generation of the name for this particular mission. This is for a spacecraft that will demonstrate formation flying in space. The intent is to show that you can use many spacecraft that are in a coordinated formation, so that when you fly around an asteroid, for example, you can do multi-point science data collection with multiple spacecraft simultaneously. And this one is intended to also launch in late 2021. And this one also has a propulsion system on board. Obviously, you will need that for maneuvering around each other and also for the spacecraft to maneuver around a future target of interest, such as an asteroid or something of that sort. But this is a natural progression of abilities of all these spacecraft that we think we might be able to use these technologies in the lunar orbit. And we will be using a laser and a reflector on board the spacecraft to fly over a number of the craters on the moon, particularly in the South Pole. And we will laze the craters, and the reflection we get back will give us an indication of the amount of water ice that is prevalent in the bottoms of those craters. And this one is, as I mentioned, is intended to launch in late 2021. And we'll do a number of orbits around the moon collecting this data with a 6U size spacecraft. So we are able to demonstrate now that we're using U-class or CubeSat class missions for doing Cislunar science. Even though this is still considered a technology demonstrator, the scientists who are working with this are very interested in getting some results from the laser and the reflectometer on board the spacecraft. Let's spend time talking about the one on the right called Capstone. And of course, that's an acronym. Cislunar Autonomous Positioning System for Technology Operations and Navigation Experiment. It's a mouthful, but if we are intent on providing a sustained presence on the surface of the moon, we intend to build a new space station that will be in a particular orbit that operates in cislunar space, and that orbit is called a near rectilinear halo orbit. And this spacecraft here, which is about 18U in size, will be launched early next year, and we will be using a number of gravity assist maneuvers because this is only an 18U spacecraft. And we intend to put the spacecraft into the near rectilinear halo orbit to help us characterize that particular orbit, because no one has flown in that orbit before. And it's a very interesting orbit to be putting a space station in. So we want to characterize the orbit before we actually start building the gateway space station in that orbit. Now, you can probably do a bit of Google on this to find out if you're curious about the near rectilinear halo orbit. But we will be ranging with this spacecraft using our DSN, or Deep Space Network, on Earth. But we have today a spacecraft that has been orbiting the moon since 2009 called the LRO, the Lunar Reconnaissance Orbiter. And we'll be ranging the Capstone vehicle with that particular spacecraft as well, as it is orbiting the moon, so that we can help characterize the orbit that the Capstone spacecraft will be going into. This is considered still a technology demonstration, but it is also, if you will, a precursor to the building of the gateway into an orbit that we have not flown in before. And so we want to make sure that the orbit is as stable as mathematics indicates that it is. So this was a quick overview of the Small Spacecraft Technology Program. As I mentioned before, the intent of my office is to take technologies that are either in the power, propulsion, communications, or processing areas, get them to where their technologies are more mature as they're coming out of different areas, whether they're academia, other NASA centers, small businesses, or even in public-private partnerships between NASA and large businesses, and get them to where they're mature enough that you can actually use them with a sense of maturity that they will be well relied upon for conducting science or exploration missions in the future. And this is just a quick chart on our schedule. As you can see, we have a lot of missions that will be going on over the next couple of years with CPOD, Pathfinders 1 and 2, CLIC A and B and C, the Advanced Composite Solar Cell System, Starling, and Pathfinders 3, 4, 5, and 6. And those will all be going on over the next couple of years. So my office, actually, we stay pretty busy. Now, I'd like to switch to the Kepler mission. I was the program manager for this mission for a number of years before the center director asked me to move into the small spacecraft technology area and start working on a number of technologies coming out of that, because that former center director really viewed small spacecraft as part of our future. But nevertheless, I still see this is one of the more noble missions that NASA has conducted. I won't say that it ranks up there with Apollo, but it is easily considered one of the great observatories ever built. We decommissioned the spacecraft in November 2018, and it had one pure scientific objective, and that was to assay a part of our galaxy and determine the extent and the class of exoplanets that are out there. Of course, when you were using a spacecraft like Kepler and you're looking for planets, the chosen method for looking for the planets was something called transit photometry. And it's a very simple concept. You stare at the stars and you wait for the planets to go across the face of the stars, and you measure the change in brightness of the stars. And if you watch this several times, then you get an indication of the size of the planet, its distance from its host star, and its orbital period. Why was that important? Well, the spacecraft Kepler, named after Johannes Kepler, who wrote down the first laws of planetary motion, which is what we use in determining the types of planets that we detected with Kepler, and also their orbital periods and the characteristics of how far they were from their host star. The results actually very rewarding and satisfying, and I would like to talk to you about some of those in a minute. Now, the first years of Kepler's life, we stared at an area near the Cygnus constellation, near Vega Lyra, and you can see the imprint, if you will, of Kepler's field of view on that particular area of the galaxy, and that is a rather large field of view. It's huge. It's much bigger than normal ground-based telescopes that you look out there, but we needed a field of view that was rather large because we wanted to get a sampling of up to 200,000 stars to give us a good statistical analysis of what is really out there. We start talking about the family or the menagerie of planets that exist across the galaxy. We were able to stare at that field of view for the first 4 years of the mission. Kepler lasted 9.5 years, but in the third and fourth years of the mission, we lost sequentially 2 reaction wheels on board the spacecraft. And when we lost the second one in the fourth year, we had to become a little more ingenious about how we pointed the spacecraft after that, because we only had 2 reaction wheels left. And let's look at what the results were when we started looking at planets. Now, the 3 yellow dots you see represented on this field of view, and this is a full frame image from Kepler. Those 3 yellow dots represented where the first known planets were detected using other methods before Kepler launched. And by the end of the 4th year, we had found many, many planets. And of course, we were looking primarily for Earth-sized planets in the habitable zone because we wanted to find, in a romantic sense, another Earth. But as you can see at the very top of the screen, the Kepler mission counts was well over 4,700 planet candidates. We have confirmed over about a half of those now, and range anywhere from planets as small as the size of our moon to giant planets, some much bigger than Jupiter. So nature will make planets the way nature wants to make them. There is no cookie cutter. It's this is what the marvel of nature is, that the nature usually surprises us every time we ask a scientific question and we get an answer from it, and that usually leads to more questions. So this is a mission count, and I just updated this just recently. And the 4,700 you see at the bottom, almost 4,800, are the total counts that we have of candidates and confirmed planets. And the number you need to look at that's at the top of this chart is in the middle. The candidates and confirmed planets that are in the habitable zone. And there were considered to be about 300 and some odd planets that are in the habitable zone that could be potentially habitable, that could be like an Earth, but we don't know that. We just know that that's how many are potentially out there, and those are candidates and confirmed planets. So how many are Earth-sized? There's a smaller number, and there is about a couple of dozen, maybe 30 now that we detected and confirmed that are about Earth-sized. Now, I mentioned at the end of the fourth year, we had lost our second reaction wheel, and we had to repurpose Kepler into different fields of view. We had to point it at different areas using the solar wind as our, if you will, third balancing reaction wheel to allow us to point this with any degree of accuracy so that we could detect other planets. And you can see the counts on this one from the Kepler K2, we call it. Now, I've been asked a number of times what were my favorite discoveries from Kepler, and these, and I will talk about that momentarily as you look at the results that we're having for all exoplanets now that have been discovered. And the numbers are astonishing. And there was another spacecraft called TESS that followed Kepler, and it was looking for planets in our own stellar neighborhood with 35 out to 100 light years, whereas the Kepler spacecraft was focused anywhere from 1,000 out to 5,500 light years from us, peering far and deep into the galaxy, whereas TESS, the follow-on to Kepler, was looking more in our own stellar neighborhood, looking for Earth-sized planets in the habitable zone. And there have been a number of planets also detected by TESS, and the confirmation numbers, I'm sure, will go up. I think two of the most interesting planets that have been detected by Kepler, and my favorite ones, were Kepler 22b, and that was only because it was the very first one that we detected and confirmed, and it was a super Earth-sized planet. And it was detected within the third year of the mission. And that one was my favorite only because it was the first. And the second one was detected by Kepler during its K2 campaign after we had lost 2 reaction wheels. And that one was called Kepler K2-18b. And why is that my favorite? When we found that planet, we actually turned 2 other telescopes toward the planet to see if we could learn more about it. And we used Hubble and the Spitzer telescope before Spitzer was retired. And we're able to detect water vapor in the atmosphere of Kepler K2-18b, which to me was an astonishing discovery because that is the first time that we have confirmed water vapor in the atmosphere of another planet that is beyond our solar system. Now, the image that you're looking at here is one of the last images that was taken by Kepler, and it's well saturated because it's a very bright target that we were looking at. And what you're looking at is Earth from about 96 million miles away as Kepler was drifting away from Earth as it follows us around the sun. Earth takes about 365 days, of course, to go around the sun, and Kepler is a little slower than us, taking about 371 days to go around the sun. And before the Kepler spacecraft ran out of its final propellant, we were able to turn the Kepler spacecraft and do this image of Earth. Of course, it's so bright because the Kepler photometer is such a sensitive instrument that it saturated a number of the circuits on board the photometer. But we wanted to do a selfie, if you will, of a Kepler looking back at the home world that gave birth to it before we decommissioned it and turned the spacecraft completely off. I know there are a number of students that are observing this talk today, and I have a particular challenge for you. In September 2060, Earth is going to go right by Kepler again. We're like two runners on a racetrack, with Earth going around the sun every 365 days, and Kepler, the slower runner, on an outside path, taking 371 days. But if you do the math, you would find out that in September 2060, Earth is going to go right by Kepler. And I would like the students around today would perhaps make a commitment to go up and retrieve the spacecraft and bring it back and put it in the Smithsonian. This is one of my favorite selfies. This is a view of Earth from Cassini. And we have taken only a few selfies with our spacecraft that have moved into the outer parts of the solar system. And this one was taken by Cassini in the year 2014. And it gives you an indication of just how small we are, because that's the Earth system, Cislunar system, from a distance of about 1 billion miles. And I'd like to talk a little bit about the impacts on the environment of our human civilization, because someone earlier brought up COVID-19, and we can actually observe the indirect impacts of COVID-19 on the Earth. But this one, before I talk about COVID-19 impacts on the Earth, I just want to share this photograph with you. This was taken from the International Space Station by one of the astronauts. And the green lights you see, yes, the green lights you see are fishing fleets on the Gulf of Thailand. And you can see how wide scattered they are, because they're using these green LED lights to lure the fish up from the depths, and so they can catch more of the fish. The COVID-19 impacts, see a reduction in air pollution in certain areas because of shelter in place. And so you saw less transportation and less movement of human beings around the surface of the planet. We can actually see this, and here's some images from India, and this is from the northeastern United States. And so you could see a change in air pollution as a result of less human movement across the planet as a result of shelter-in-place activities. Now, I just want to share with you two more images, and there are a couple of exciting events coming up later this week. You're going to see the first the return to space of American astronauts being launched from U.S. soil for the first time in 9 years. And you can see the Falcon 9 rocket on the left, and of course it's going to be carrying the SpaceX Crew Dragon capsule up to the International Space Station. And there's one other one I'd like to share with you. And about 6 to 8 weeks from now, we'll be launching our next rover to Mars. And this one is a little bit bigger than Curiosity. This one's called Perseverance, but this one also has a unique technology demonstrator on it. And it's a helicopter. And I'm going to run an animation. It only runs about 60 seconds. So I'm hoping that you'll be able to see this particular animation of the first time that we will have flown a helicopter through the Martian atmosphere. This is not meant to be a significant science demonstration, but it will show that we will be doing a technology demonstration on the surface of Mars with a rotocopter that is solar powered, and it just charges its batteries before it lifts off and flies to a distance. So I'll let the animation run just for just a few seconds. As it lifts off, of course, we'll be observing it with the cameras on board the Perseverance rover. The copter itself has the name of Ingenuity. We launch in in July, and then we'll be landing on Mars in February. And one more item, as before I take questions, and this one is OSIRIS-REx spacecraft that is orbiting the asteroid Bennu. Later this year, it will be doing its final touchdown or touch and go maneuver across the Bennu surface of that asteroid, and we intend to capture material and bring it back to Earth. So I will leave it at that. Just I want to bring up some highlights of upcoming missions as I conclude the talk today on NASA small spacecraft and also on the legacy of the Kepler mission. So I think thank you for your time, and I think we have a little bit of time for questions now. Is that correct, Honma?
Yes, sir. Yes, sir. Yes, sir. Sir, as you know already that more than 1,400 participants have registered for this webinar. It is one of the greatest thing. We didn't expect that much participants will be coming for this webinar, and unfortunately we are having a WebEx limit, so we have streamed that live in YouTube as well as Facebook for other participants. So we are receiving many comments from them and also as well as questions. So I request our participants are in WebEx itself to ask the question in the chat itself. So we will be asking one by one to Roger, sir. Sir, one of the question from Radhakant Badi, a professor from Indian Institute of Science. He's a professor from Indian Institute of Science. So he asked about if small satellite missions are done, so it will be going to add a debris problem, right? So how NASA is going to work on those space debris? If we are
Space
going
debris?
to,
Oh, on space debris?
yes, sir. If you are launching on small satellites, more small satellites, so he is
Yes.
asking about yes.
Yes, that's a really good question. And it remains a concern, not just for NASA, but for commercial businesses that are also wanting to place more spacecraft in orbit to extend their business models into space. As you may know, that the company Planet orbits a number of spacecraft around the Earth today, and they're all just 3U in size, and they use those spacecraft to service their customer base. And as you also are aware, the SpaceX has begun launching its constellation of space-based internet service. Those spacecraft called Starlink. So the sky is getting kind of, if you will, crowded. And so we think there should be a collaboration among a number of countries about what to do about this so that we can have space traffic management just as we do air traffic management through this, the aerospace today for airplanes. In the Federal Aviation Administration in the U.S. manages air traffic management across the U.S., but there needs to be an international activity to manage space traffic management for the commons. In the U.S., I think it's Department of Commerce, which is an interesting selection that has been given the direction to start working on the activities for tracking all these space, because the more that you put up there, the likelihood of collision goes up. We've already seen some collisions. We are starting to put, I call them barcoders, if you will, on a lot of our spacecraft, so that you can illuminate the spacecraft, so you can see which spacecraft are you tracking, so you can get a better idea of where it is for the duration of its lifetime. In my particular area for technology demonstrations, our intent is, once the demonstration is complete, get the spacecraft out of orbit. Just get it out, because we don't want to leave it up there. And that's what my organization is starting to do for all of our technology demonstrations, is provide a means to drag the spacecraft out of orbit or leave enough propellant on board that you can deorbit the spacecraft immediately after the technology demonstration is done. But I think there needs to be an international movement towards creating a space traffic management activity as the same way that we manage air traffic across a number of our countries today when we're managing all the airlines that are moving around. So it's still an area that is, I think, weak. It needs to be improved. It needs to be strengthened. Otherwise, I think we're going to experience more collisions in the future. And if you're familiar with the Kepler syndrome, if you get collisions between spacecraft that beget more collisions, but that beget more collisions, then we end up denying the use of space to everybody because of the junk that is, and the collateral damage that's been created by these collisions. But it is a serious question for us to start looking at, and we need to start having some serious answers and ways of better managing the small spacecraft traffic and large spacecraft traffic for that as well.
Okay. Everyone has, many people have asked the same question, sir. I hope they got the answer from you or answer itself. Another question is from Elisa. According to Einstein relativity theory, if we travel in speed of time, the mass will be changed. Is it true?
Oh, Einstein's theory of relativity. If the faster you approach light, the mass increases. I don't know if I can. I don't know if I understand the point of the question. Is, do I agree with Einstein? I don't think I couldn't agree. I couldn't disagree with Einstein.
So another question from Manav. Why is NASA not reconsidering the Sea Dragon rocket for Mars missions? Sea Dragon rocket.
The Sea Dragon
rocket, Sea Dragon rocket for Mars missions.
Oh, well, I don't think it's out of the equation. We are looking at, of course, NASA is working on Artemis 1 as the means for lifting rather large payloads into orbit. We need the mass to build a space station with. We collaborate with Elon Musk and SpaceX quite a bit. So, as a matter of fact, we buy his Falcon rockets, and the Air Force, the U.S. Air Force, is also buying Elon rockets as well for conducting some of its missions for getting some of its payloads into orbit. Of course, the Air Force doesn't have any interest in Mars, whereas NASA does. And we will, I'm hoping that we just look at the opportunities in the future and whatever best suits the needs for getting our payloads to Mars. That's the one that we should pick. I'll be diplomatic in my answer.
Yes, sir. Question from Rajat. Why does NASA and other governments hide the presence of extraterrestrial life, UFO, from general public? Why they are hiding?
I don't know of any official efforts by NASA to hide that. Matter of fact, I'd love to find extraterrestrial life because I think my budget would go up.
Yes.
It's an interesting question because I know that there are a number of organizations out there that talk about UFOs and things that have been seen or not been seen. And, scientists I work with in NASA, none of them could keep a secret. They like to talk and they like to write. And so if they have evidence, I'm sure that they're going to write something to get it peer reviewed because they want to be the first to reveal something like that. I worked with a number of scientists on the Kepler mission as we were looking for another Earth. And there was a lot of competition among those scientists to be, get the first paper out that wrote about the first Earth 2.0, if you will, that was going to be discovered by the Kepler mission. And those scientists couldn't keep a secret if you paid them $1 billion.
Okay.
My question, being an Indian, I'm more concerned about ISRO. So, what is your take, NASA's take on ISRO's programs and how they look at the ISRO program?
I'm sorry, repeat that question. I missed.
Yeah. My question is, being an Indian, what is NASA's take on ISRO's program?
On international programs?
Yeah, ISRO, Indian Space Research Organization. What the programs they have on Mars? And what is your NASA's take on it?
If you ask me, I'm in favor of them. I don't think we have the budget to do what we would like to do, and I'm in favor of international cooperation up and down the line. You have to talk to the powers that be that are above my level, though, when it comes to international collaboration and cooperation on missions, but I'm in favor of it.
Okay. Actually, he asked, what is the view of NASA about ISRO? What is the view of NASA about ISRO?
Oh, about ISRO. Oh,
Yes.
I think they're impressed with ISRO. I know you've had some successful launches. You've also had some disappointments with a lunar mission. So have we. We've also had some missions that failed as well. And so, as we like to say, this is rocket science. It still is. And
Yes.
you're going to have some failures along the way. And we did too. Israel will have some failures. The Japanese Space Agency will have failures. This is not an easy business to be in, but it is challenging. And it also, when you have failures like that, you learn from them. I think that NASA has an excellent view of ISRO, of the Indian Space Organization.
Thank you. Thank you.
What are your views of both Starlink satellite?
I'm sorry, repeat the question.
What are your views about Starlink satellite? Starlink satellite.
The Starlink, oh, yes. Well, I know that a number of astronomers are annoyed by Starlink because it a lot of reflections off the spacecraft, and it sort of it interrupts their observations from the ground. But Elon Musk is plowing ahead, and I don't know how far along he is with populating his entire constellation, but there are a number of astronomers that I have read about that are, as I said, very disappointed and concerned with if another phrase for it is the light pollution you get by all the reflections that they're seeing off of those spacecraft. I have gone out several times at night to see if I can see them moving across the sky, but I have not been able to do that yet. But I know of a number of people where I work who've been able to, with the naked eye, see a train of Starlink satellites going across the sky. But the ground-based astronomers are somewhat annoyed with Elon Musk about that right now.
Okay. One question from Prabjot. Are you involved in DM2 mission?
I am not, but I will be watching. I'm looking forward to that. And then NASA has, if you want to go check on the nasa.gov website, they're also inviting, as we're doing a webinar today, NASA is inviting for you to be a virtual observer when this launch happens on May 27. It'll be at 1:33 p.m. Pacific time, California time. So it'd be early in the morning in India. If you have nothing to do and you have a night of insomnia, you can't sleep, you want to get up and watch the launch, I'm sure you'll enjoy it from India, because that's as I said, it's the first time we will have launched U.S. astronauts from U.S. soil since 2011. But I'm looking forward to it. There's a number of events coming up for NASA, and that I indicated at the end of my talk, besides Crew Dragon Demo 2, and we also have the launch of the new rover that's going to Mars, and the window for that opens on July 17. Then in August of this year is when the spacecraft OSIRIS-REx does its final touch to the asteroid Bennu to collect some residue from the surface of that asteroid, and then begin its journey back to Earth to bring that residue back for analysis here. So there's some upcoming exciting events in NASA over the next few months.
Okay. So in addition to that, we are organizing a session on during the launch on May 27 in the midnight. Yes. So
wow.
we are trying to bring a guest of founder member of SpaceX. We are
Excellent.
Yes, sir. So our audience or our students will be engaging in that also. I hope it is a midnight in India. I hope our students will be engaging that also. Coming back to the QA, can NASA have any spacecraft to protect the Earth from asteroids?
That's a really good question. There is the former administrator for NASA was asked that question when And his response, and it was in front of a committee of senators in the U.S., and he was asked about, protection against asteroid strikes. And basically he says, we don't have that capability today. And if you think about what happened over Chelyabinsk in Russia a few years ago, that asteroid strike that came in and it disintegrated before it hit the surface, and it had a very low angle of trajectory, about 10 degrees. If it had been a higher angle, anywhere from a direct strike like 75 to 90 degree inclination, Chelyabinsk would not be here today. So I was hoping that that would be a wake-up call in some cases. Now, NASA has increased its abilities in working with a number of international partners to be able to track more of these NEOs, they call them, near-Earth orbiting asteroids and targets, so that we could get a little better warning if something that would be a size enough that it could cause some serious damage on the surface of the Earth, that we could detect it beforehand. But what will our response be? We don't have a way to counter that right now. Now, NASA is working on some technologies matter of fact, we're going to go off to an asteroid and do a strike on it to determine how much of the orbit of the asteroid can we move with a strike against one of these. And I don't have the details in front of me, but you could, if you're interested in this, you could go read about this particular activity that NASA has ongoing. But of course, if you talk to some people, they want to just send the nukes after it, send the nuclear weapons, and blow it up. But I mean, there's all kinds of ways that you could address that. It's just that we need to be more mindful of having the capability to do so, because there is an asteroid out there that probably has our name on it. We have plenty of, we have strikes before that hit the planet Earth. You see the craters that are around the planet where we've had asteroid strikes in the past. And Chelyabinsk was the latest one that was a wake-up call for us. But if you ask me today, if we saw an asteroid coming at us today, could we do something about it? We don't have anything in the arsenal right now to go, and we should be thinking about that.
Okay, sir. So there are many questions coming up. Since we are having a short span of time, I will be concluding with 2 questions. And remaining questions I will be sending through mail to you. So if you have time, you can answer for this. We will share with the audience also.
Okay.
So one of the question is, what about the calculation on solar winds during Kepler missions?
Calculate on the solar wind in the Kepler mission?
Yes.
Oh, yes. That was, never underestimate a NASA engineer. When the second reaction wheel failed in the 4th year, there was a lot of disappointment within the Kepler team. Even though the mission was scheduled to last only 4 years, we were collecting such good data that the NASA administrator and also his staff were delighted with the results from the mission. And when the second reaction wheel failed, there was a lot of disappointment because we knew we would find many more planets. Well, for a number of months, we worked on what can we do to recover the spacecraft, and we did a number of experiments, even with the wheels themselves, trying to recover them. But it was the engineer at Ball Aerospace Corporation that worked with us to build the Kepler spacecraft came up with the idea of using the solar wind as a balancing wheel, if you will, against the solar panels. Because if you look at the solar panels on Kepler, they're fixed and they're symmetrical. And if you turn the solar panels and lay the spacecraft on its side, you can see that the solar wind sort of splits evenly as it hits the spacecraft, and we sort of use that as a balancing activity using the other 2 reaction wheels. It meant that we still could not point Kepler at the original field of view. We had to point at different parts of the galaxy, and every about 85 days, we had to repoint the spacecraft that sunlight would not get into the telescope, because the photometer is so sensitive. If sunlight get in there, it would have cooked. It would destroy the photometer. That would have been it. So there's a couple of good papers out there that were written on that activity, and if the questioner has some detailed interest in that, sure you could do an internet search for that particular information, and I'm sure there's a good engineering paper that was written by the engineers that came up with that idea.
Okay. One question, can we place a fuel station at neutral point between Earth and Moon to refuel the spacecraft? Is it possible? Refueling of spacecrafts?
Yes, that is possible. And there is, matter of fact, a business company recently, and I think it was Maxar Technologies are demonstrating that. NASA has a demonstration in the works called Restore L, in which we would intend to go up to a spacecraft and refuel it. But when you think about that, you have to build that capability into the spacecraft from the beginning, so that you could intend to go up there and refuel it. Because if you don't, then where are you going to stick the hose? If you think about it, the hose, if you go up there and the spacecraft has not been pre-configured for this. But I think we're starting to see some ideas among even commercial companies, particularly if they have larger spacecraft, particularly for those that orbit in the geosynchronous belt, because those are rather large spacecraft. And if you're able to refuel those, then it may be more cost effective to do that as opposed to replace it with a brand new space vehicle after it runs out of propellant. So you're starting to see commercial companies are doing technology demonstration of this. NASA is about to do it with a mission called Restore L. So I think you're going to be seeing more of that in the future. There was, I think another thing you could, along the same line, even though it's not exactly the same, is we're moving into an era in the not too distant future when I think we will be manufacturing and assembling spacecraft on orbit. I am trying to convince NASA right now of doing technology demonstration within the next few years of that, even though it'd be on a very small scale, using just CubeSats. But that's how you start these big projects sometimes, that you do it on a small scale. NASA awarded from the NASA Innovative Advanced Concepts Group just 2 years ago to Cornell University, Dr. Dmitry Safransky, a concept on how would you use small spacecraft technologies to do on-orbit assembly of a large aperture. And why is that important? Look at the James Webb Space Telescope, which is, though it's over budget and behind schedule, that is the largest telescope, when we launch that thing, that we will have put into the fairing of a rocket. And we have to fold that thing up like an origami to get it to fit. We don't have any fairings that are any bigger than that one right now. And so if we want to get to these apertures of these space orbiting telescopes that are bigger than 6 meters, we're going to have to come up with something a little more clever. And that was one of the things that John Grunfeld, a former NASA astronaut and also former head of NASA science, challenged a number of scientists at a think tank to do one time, because he was quite interested in the results that were coming from Kepler. He said, when can we get to a telescope that's big enough that we can actually image some of these extrasolar planets within our stellar neighborhood? And the estimate is that that aperture has to be about 40 to 45 meters across. That's a large telescope. And so I think that in the students who are on this telephone call today, your generation is going to figure out how to do that. You're going to manufacture in orbit, and you're going to assemble it in orbit. And that's what I challenge some of the students that I visit when I go around different university campuses in the United States. I encourage them to work on that concept, because when you think about the pale blue dot that we have seen with the Voyager spacecraft and also with the Cassini spacecraft, one day we're going to have a orbiting telescope that is big enough that we will see more than a pale blue dot for an extrasolar planet that's within our stellar neighborhood of 25 to 50 light years from us. That will be an amazing event.
Yes, sir. Okay. So last personal question, and I will end with that. We are having some open source softwares available in NASA, right? Sir? Open source softwares. So if
go ahead.
Suppose if any of Indian students or any other foreign country students, if they are working with that particular software and developing some project, whether NASA will accept that?
I don't know. I don't know the protocols for that and how that works. I was reading some interesting history yesterday about the Apollo software, and it has been put on GitHub. And all of the, even though it's very old, it's that software is 50 years old. But I was amazed that that NASA put that on GitHub so everybody could take a look at it. What was interesting about that software, because I was reading the history of the young people that actually built the software that was used on Apollo. And that's why I'm so glad that you invited me here to this university, because I know there are a lot of students that are on this telephone call or on this webinar today. I want to speak directly to them, if I may. The average age of the NASA workforce when we went to the moon with Apollo was 28. 28. Don't tell me that young people don't make a difference. They always have and they always will. And I was reading some of the history yesterday about the Apollo mission, and this is dramatized in a couple of movies, but it was also in the documentary about the Apollo mission, as Armstrong and Aldrin were making their descent onto the lunar surface. They kept getting this alarm called the 1202. And Houston Space Flight Control were worried, and you can actually hear the concern in Armstrong's voice when they were saying they kept getting this alarm. And so immediately Johnson called MIT, because MIT, we were working with them to build the software for the command module computers and processors. And it was a 25-year-old student who responded and said, the 1202 alarm, don't worry about it. The computer is doing what it's supposed to do. So having said that, the youngsters and always make a contribution. They've always made a difference. And I'm hiring more youngsters today to bring them into NASA Ames Research Center, because that's our future. They're the ones who are going to conduct these missions in the future. I'm enjoying the results of those who came before me. And I'm hoping that we will continue to have students that are interested in space missions, because they're going to be the ones that are going to invent the future. They're the ones that are going to invent these telescopes that we talked about today. They're the ones who are going to create the next missions that go out to do science and exploration. And I hope that they are the ones that are going to help us address the existential crisis that we are facing today when it comes to climate change and also biodiversity collapse. So I will close on that, but thank you for your time today. It has been a pleasure speaking with all of the staff, faculty, and students at your university.
Yes, sir. Thank you, sir. Thank you very much for giving your time also. Surely Chandigarh University will collaborate with some projects with NASA, and we will also contribute to for the humankind.
Thank you.
Yes, sir.
Thank you.
I
Thank you
request
very much, sir.
HOD sir to give the vote of thanks, and also I request the participants to stay there. I will explain the procedure for certification. So I request HOD sir to give the vote of thanks.
Thank you, sir, for your wonderful topic, and it was very informative and beneficial for all the aerospace engineers who are pursuing and who are already in this field. So thanks a lot. We look forward for your like this webinars in future also, and hopefully we will work together, and we will be in constant touch with you for any help and for any advice from your side. Always will be appreciated for our community, space community. Thanks a lot, sir. Thank you for spending valuable time. Thank you very much.
Thank you. I appreciate it. Thank you very much.
Yes, sir. Thank you, sir. Thank you. So I request the participants to stay there, and I will explain about the certificate procedure, and we can proceed over.
All right. Thank you.
Yes, sir. Thank you, sir. Thank you. I hope you can see the screen, right? HOD, sir?
Yes, yes, yes.
Yes, okay. So for certificate generation, more than 1,400 people are there. So I request those who have attended the lecture, kindly enroll yourself in this platform, academy.bigsofero.in. So create a new account, right? So while creating a new account, you have to just enter your username, password, and email address, confirmation for the same email address, and your name. According to your first name, the certificate will be automatically generated. So you have to make sure the first name is correct, right? And as well as if you see the one second, sir, one second. There is a problem over here. Okay, so those who are not able to see, I will. We are having a video also. We will share with the participants. So those who are able to see, kindly go through that. Okay. So create a new account, and after creating a new account, there will be a password will be sent to your respective email IDs. So after that, you can sign in, and you can go to the lecture of today's lecture by Roger Hunter. There will be a the poster, chemistry poster. So you have to just find that NASA small sat. So after clicking over there, it will enter into the page of Chandigarh University, Mr. Roger Hunter lecture. So right now you can able to see the lecture feedback and lecture certificate, right? So now you can access right now. So I request all of you to sign in into the academy.wingsofarrow.in and give your valuable feedback. Once you submitted the feedback, the lecture will be the certificate will be automatically generated, and it will be mailed to your email ID also. Okay, you can download from here also, as well as it will be in your mail ID also. Okay. So this module will be open for 1 day, so you can download at any time. So after 1 day, it will be locked. Okay. Thank you for very much. And we will send this same procedure of downloading certificate in your mail also, so no need to worry. And I thank HOD sir, Dr. Dharmendra Singh, and as well as EC HOD, Dr. Paras Chawla sir, for their contribution towards this webinar. As well as I would like to thank our Honorable Vice Chancellor and our Honorable Chancellor and Vice Chancellor, Pro VC sir and Registrar sir for their constant support. And our next webinar will be on 27th, same May month, in the midnight around 1:30. We are live telecasting the SpaceX launch, SpaceX and NASA's crewed mission. We are trying to bring one of the founder member of SpaceX. So I hope we will be doing that webinar, and I request all the participants to join over there. So right now we are signing off from here, and I once again I thank all the participants, and we are signing off. Have a good.
Thank you.
It is night, so I can say good night and
Good night. Good night.
Stay safe.